This is Solomon Abdallah doing his capstone lab presentation for Chem 204 lab section 202410. For this lab, I have decided to do a spectral analysis and structural determination for the molecule ethyl butanoate, which is a molecule I picked and analyzed for the Fisher esterification lab we did a few weeks back. I thought it was interesting that this is a molecule, or one of the molecules responsible for the sweet scent of pineapples, or also I found that it could be considered a scent of mangoes online. So let's get into it. The molecular formula for ethyl butanoate is C6H12O2. It's a fairly simple molecule. Its molecular weight is 116.16 grams per mole, in line with the formula. Room temperature is a clear, colorless liquid with the odor and taste of pineapples. Its boiling point is 121.5 degrees Celsius. Its melting point is negative 98.0 degrees Celsius, explaining why it's liquid at room temperature. Its density is 0.87 grams per mole at 25 degrees Celsius. And is insoluble in water. So if you created a mixture of this molecule and water, you would see two different layers, with this layer sitting on top of water. Again, it is lower density and insoluble. There are no bonds capable of hydrogen bonding, that is, no NH or OH or fluorines in the molecule. So no hydrogen bonding. The mass spectra, it indicates an M peak at 116 mz, or mass units. This falls in line, if you're working backwards from starting with knowledge of the structural formula, you can see that that follows that 6 carbons at about 12 grams per carbon is 72. 12 hydrogens at about 1 gram per hydrogen is 12, and 2 oxygens at about 16 grams is 32. That adds up to 116 mass units. But if you did not know the formula already and you had to work backwards from knowing the M peak, you would see that with an M peak at 116 and knowing that there are 2 oxygens, you would subtract 32 from 116, get about 84. You could factor 12 into 84 two different ways, with 7 times 12 would be 84 exactly, leaving no hydrogens, which wouldn't make sense. So if you subtract 12, subtracting one of the carbons, adding 12 hydrogens, you would have 6 carbons, 12 hydrogens, and can't forget about the 2 oxygens, making a molecular formula of C6H12O2. The IR spectra indicates the functional groups sp3 hybridized CHs in the alkyl region at just shy of 3,000 wave numbers, or inverse centimeters. There's also a carbonyl C double bonded O present at about 1738 wave numbers. Knowing the formula is O2, and looking again at that double bond to O, it's actually in the right region for an ester functional group. So we're going to roll with that. The hydrogen spectra is very, very difficult to analyze, but we're going to do it anyway. There are 5 unique chemical environments indicated by 5 peaks on the spectra. Starting with most upfield peak, we have a 3H a peak indicated to 3 hydrogens at about 0.96 parts per million. It's a triplet, therefore it must have 2 neighbors. This kind of shows that it's a methyl group bonded to a CH2 group, so it's probably at the end of the molecule. The next peak also integrates to 3H, 3 hydrogens. It's also a triplet, So it's bonded to 2 CH2 group, and it's located at 1.256 parts per million. So this also suggests it's probably a methyl group at the end of the molecule. The next peak at 1.65 parts per million integrates to 2H, so it's also a sextet. So it neighbors 5 hydrogens. It neighbors 1 hydrogen, 1 group that's probably a methyl group, CH3, and it also neighbors another group, which is probably CH2. So we see that the molecule has a propyl group from that interpretation of these peaks. The next group downfield is at 2.27 parts per million. It integrates to 2 hydrogens. It is at as a quartet. Actually, I wrote triplet, but it's actually a quartet, so it's bonded to a methyl group. Actually, it's a triplet. I got that right the first time. So it's bonded to a CH2 group. So we know, and it's in the region of a hydrogen bonded to a carbonyl carbon. So we know that we have a propyl group bonded to a carbonyl carbon. That's half the molecule. Finishing up, we know there's another methyl, but now we see that there's another CH2 group. That's a quartet, so it's bonded to the methyl. It integrates to 2 hydrogens. It's at 4.126, which is a region where hydrogens on carbons that are next to the O of an ester group. So we see an ethyl group bonded on the other side of the ester group, giving us the entire structural structure of the molecule ethyl butanoate. Again, this is a pretty difficult spectra to analyze, but we did it. Structure determination and spectral analysis. In conclusion, we have from the mass spectra the chemical formula of C6H12O2. We have the IR spectra gives alkyl and carbonyl functional groups, and also a C single bonded to O indicates that it is an ester. The NMR gives 5 different unique chemical environments for hydrogens. And here is what the molecule looks like in skeleton formula, ethyl butanoate. Here are the references from the online database where I found all the spectra. And that concludes my capstone project. I had a great semester. Thank you, Professor Mohammed. I really enjoyed lab.